one thing that's really helpful, a way of thinking about model building, is to draw pictures of the simplifying assumptions in a very specific form. That is to say, you just draw a picture of your chain rule that represents your joint probability distribution, basically whose nodes are the random variables that matter in your model. Okay? And then the edges represent conditional probability relations. Basically, if a pair of variables appears in a conditional probability term in the expansion of your joint probability, then you're going to draw an edge from your condition to your subject variable. Okay? There's going to be an edge with an arrow on it. It's a directed edge because conditional probability is asymmetric, right? It's a relation of a condition to a subject, which is not the same as the converse. Okay? So we're going to draw these pictures, and the number of edges that appears between a set of variables is basically going to tell us whether we've achieved any dimensional reduction or simplification versus the fully general chain rule. All right. Well, this all sounds very abstract, but when we go to real problems, yeah, it becomes concrete. You have to say, oh, here's this problem. How would you draw that problem? How many edges are you going to put on it? So let's just, for three variables, there's not very many possibilities, right? You can have all three possible edges. You can have only two edges. You can have one edge or no edges. And each one of those pictures corresponds to a specific form of the joint probability distribution, right? Here's the fully general chain rule. It is always true that this equals that. Any complicated probability distribution is always valid to factor it in this way. That's just the fully general chain rule. Here's a situation where we are asserting that y and z are what? Conditionally independent given x. It's important for us to specify that condition, that they're conditionally independent given x. They're not independent of each other because they are connected by something. So these two variables could be highly correlated with each other, but the assertion here is that that correlation or connection between those two variables is solely through x. There's nothing else that connects them other than x. And that corresponds to writing down a form for the joint probability in which basically y and z need not ever appear in the same term of the factoring, right? There's a term that's got y and x, and there's a term that's got z and x, but there's no term that has to have both y and z in this particular order of expansion, okay? We could say that actually z is independent of x and y. Okay? So now x and y are connected to each other, but z is just statistically independent of both x and y. And in the last scenario, we just have three independent variables. Not very interesting, but that's the highest degree of independence that we can possibly have for three variables. Okay? So it's a simple idea when you apply it to three variables. It has implications for what you might think of as the computational complexity of the model. That is to say, if we want to store this probability distribution, well, there's no way to factor this to reduce the computational complexity. This term here is itself a three-dimensional object. To store that probability distribution, we're going to have to allocate, a table whose size is going to go as order n cubed if each one of these variables had n discrete states. Okay? Whereas, if we have a problem like this, where now we can get y and z to be conditionally independent given x, we're only going to have to write down two-dimensional objects, right? There's one two-dimensional object, there's another two-dimensional object, therefore our total memory or compute time for doing computations on this probability distribution is going to scale only as order n squared. And in this case, we'll be able to reduce this, just 3 independent problems, each with computational complexity order n. So it's order n. Question?
What would you say n represents in complexities?
So what I was assuming here was that each one of these variables had n discrete states. So when I look at a term like this, I have, n different values here versus n values there, and I'm going to have to store order n squared probabilities to represent that set of all possibilities. Here I'm going to have order n cubed values that I'm going to have to store to represent that term.
In the second case, you mentioned that y and z are independent given x.
Y, right.
So in the third one, how would you say, what would you say about the independence of y and z with respect to x?
So here, y and z are independent, full stop. No need to say conditionally independent. It's just independent. X and y are not independent.
The same goes for x and z. They are just independent.
X and z are also independent, yes. So, there's a very simple principle in these pictures, but I think you'll find that there are useful tools for how to think about building probabilistic models. And we'll practice that today. Okay. So we're generally aiming, when we say we want to build simplified models, we're aiming to build information graphs with fewer edges, right? That fewer edges means a model that is simplified relative to the fully general chain rule. We've reduced the dimensionality of the problem if we have a model with fewer edges.